Yes. Oh, good. Should write it. Okay.
CA already went abroad.
Yeah, I know. So he told me that he's leaving Thursday or something, right?
Yeah, we wondered if he finished his semester.
Ah.
We wondered, and we don't.
But he said that he still has something, right?
Supposed to.
Yeah, he said that after coming back, he has to teach. That's what he said.
Oh, okay. So he will come back.
I think so. So maybe, may I speak? May I start now? Okay, so today I just want to start with something related, but not really so much directly related to what I'm talking last time. So this is something related to this Jacobian ring. So last time I considered following. So I have a function f. Maybe f is a polynomial from this x1 to the xn. And then we consider the usual Jacobian ring, which is actually defined by quotient of this by the ideal generated by all partial derivatives. And so we call it Jacobian ring. Maybe some people call it Milnor ring. Maybe some people call it local ring. But anyway, so this one. So and then somehow we assume that this is finite dimension vector space over complex numbers. So this condition is somehow equivalent to say that the f has isolated singularities because it's a common zero of this. This common zero of these is nothing but critical points. And so if critical point has dimension, then certainly the ring of functions on critical set is not finite dimension. And if it is finite dimension, certainly it is zero dimensional. And so in this case, they are actually equivalent. And we may also consider something similar, but instead of this, we may consider ring of holomorphic functions like this. And or maybe we can also consider the germs of ring of germs of holomorphic functions. So maybe I may just like this. And take f from here. And then we can also consider Jacobian ring on this context. So just, exactly the same way, like this. And in this case, somehow I only care about the critical point at the origin. Only because I consider such a germ of functions. So now, if you have such a function f, so sometimes I speak in this side, sometimes I speak this side, but so let's suppose that this one is finite dimensional, and so Jac f is finite dimensional. Then you have a basis, right? So then this is then maybe spanned by finite many element like G1, data Gn, maybe Gk, yes, over complex numbers. And then people may call it so-called universal or maybe versal I don't know, maybe Basel deformation of this function f, or maybe so-called universal unfolding of this function f. Maybe, so I don't really give the definition of this, but somehow we consider the following thing. So here I have the basis of the vector space, Jack f, and then we may consider f, or maybe u1, uk of x is equal to f of x plus sum of ui of this gi of x, I runs from 1 to k. Maybe better to write j, maybe, I don't know, maybe j. Like this. So in this way, somehow you can deform this function by adding this, right? And somehow this term indicates that this is actually kind of universal deformation of this. So any other deformation actually somehow coming from this by pulling back something. But then somehow we have to somehow study the things maybe locally, in a sense that if you have a deformation function, then some critical point may escape to infinity. And in such a case, actually, certainly, it's a difficult. So therefore, you have to control the critical points actually stay inside some set, right? So therefore, you may have to consider some local thing in the domain here. So this is a function Cn. So therefore, sometimes you have to consider something local in Cn, so that the critical point only somehow stay inside something. And also you may also have to consider this deformation space. So this deformation space, you may also consider some small deformations, so that the critical point doesn't really escape from this. So somehow I want to tell you such a story. Okay. So the statement, it is not really precise, and I may just refer you some reference for this. So something like I don't know how to say. So this is actually this is universal in the following sense, universality. Okay. So it means the following. So if you have another space, so here actually I may just consider this, right? So I have a ck. Okay. I have ck here, and over there I have a map, a space like ck plus cross cn, and then our function is defined over here, right? Like this. But maybe I have to consider rather small neighborhood of the origin here. And then here I have to restrict myself to V cross U and containing this 0, 0 or something. Sometimes we have to consider such a local behavior. But anyway, so the universality is the following. So if you have another one, like I don't know, maybe something different, like a CA, and over here you have CA cross CN, going to somewhere like GC, so that if you restrict this G to the origin times Cn is equal to the origin function f, then CA has a map to this space CK, and over here you have CK cross CN, and here you have CA cross CN, and then there is a mapping between this. So then there is a mapping between them, which somehow, yeah, so you have a map like this, maybe, yeah. So maybe I need to also put, so we have two families, and then here, if we can find such a map, and also this map, so that they commute, so kind of pullback of fiber bundle. And so that if you have a function here, yeah, so this here you have function f, and here you have your function g. And then somehow just to precompose this to f, and then you get this g. So then we call such a thing as a universal thing, right? So if you have fiber bundle, then universal bundle is some bundle, so that everything can be obtained by pullback by this. And here we consider space of functions, maybe very close to f. And then if we have if we have a deformation of such function f, that is this guy, and then there is a map from CA to CK, this universal object, so that you have a bundle map, and G is obtained as a pullback. Such a thing is kind of a universality. And I just want to tell you the little idea how you can do this. And in fact, some of our argument somehow, was motivated by such things. So therefore, maybe it may be good. So now we consider the following. So now we consider this space CA, and then CK times CN, C, and then over here I have CA cross CK times CN. Okay. So I want to cook up some function here, this F tilde, to see how to cook it up. So I already wrote that this F is sum of this. And so also we can write G as a function of, in this form, right? Plus, I don't know, maybe as a function like H of B of U. So here I denote the coordinate here, maybe U1, UK. And here I may consider B1, BA. And so we have this. Then this F tilde is written as Fx plus sum of Ui Gix plus U of B of x, Bx. Yeah, so here is no U because G is on this, only this V and X. And then you have this H of Bx. Okay? So somehow in this case, actually we want to consider following. So here I have F tilde, and here I have V and U and X. And we want some coordinate range. So like I want to have phi, I don't know, phi 1 B. This is a map from CK to CK, and phi 2 B of maybe this is maybe CK plus CN goes to CN. So we want these things so that this one is written as a F of phi 1 of V U and phi 2 of V U X. Okay. So if u is equal to 0, then this is originally g. And so if you put u equal to 0, and then your g is actually can be obtained by pullback, right? So if you consider here, this is just phi 1, 0, phi 1, 0, comma something, and this is phi 2, 0, comma something, then you just have this. So we want to have such things. So for simplicity, somehow, I just want to consider the case at A1. Right? So just one dimensional deformation case. So let's assume this for simplicity. And I want to show that you have really such a thing. So idea is actually, maybe idea is probably you know very well, because maybe I don't know which one is earlier, but this is something similar to the argument appearing in the proof of Mozart's theorem in symplectic geometry. So just consider, if you have such a thing, then we just consider this df tilde and dv, so partial derivative in this v direction. Then, so if it exists, if phi 1, phi 2 exists, then we just differentiate this. So this one is df and duj and d phi 1 of vu. Maybe we take a j's component, and then I take this d of v plus df of dxi and d phi 2 of vux and dv. And then here the sum over j, and here sum I from n or something. So if there exists such a thing, then you have this. And somehow we want to find these things. If you have this, and then you can just think of this as the ordinary differential equation in v direction, and then you can get a flow. So somehow we want to do such things. Okay. So then I have to prepare something from algebra, and because we want to integrate something, some vector field, so therefore somehow we may have to stay, because the vector field may not be complete. So therefore we may have to stay in some local situation. And so somehow I just use this version. So let's suppose that, so we have this O, C, N, right? O, C, N, and 0 here. And then I know that this one so this is actually ideal in this O of C and 0. And this is as a complex vector space. This is actually C times this G, J, right? C times I, G, J. Okay. Like this. And we can also consider O of C. Now I have something. So now I consider A equal to 1. So therefore, 1 plus K plus N, and then maybe 0, 0, 0 or something. Okay. And then modeled by these partial derivatives. So like df tilde over dx I, and I runs from 1 to n, and then this is actually ideal in this O of C 1 plus K plus N of 0, 0, 0. Anyway, so yeah, okay. And in fact, this one can be, yeah, this one is actually isomorphic to something like this. So isomorphic to, yes, 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 yes. Isomorphic to the following. So here I have all of C1 plus K, 0, 0. Okay, so this is just, I don't know, maybe I, I wrote these three things, so therefore maybe a bit confusing, right? So I don't know how to write it. So, okay, so here this is maybe 0, 0, just first two. And then here I put this df tilde of du j, and j is from 1 to k. So this gj is actually gj is equal to df of d u j, so that I put all u1 uk is equal to 0, and then you get this. And this one is equal to df tilde, further bigger one, but I just take this uj, and then I just take v equal to 0, and u1 uk is equal to 0, right? So we have this one, and then restrict this one to here, and then I get something like this, right? I get this. So this is, because we assume that this is finite dimensional, and so this is, I take a basis here, and then I define the capital F by this formula, for therefore this is gj appear as a partial derivative of capital F by uj. So therefore you have this, and then the other one is also. So in fact we have this element in here, so that if you restrict it to here, to this Cn, then you get this. So I mean, so this one restrict to here. Yeah? So this is actually to v equal to 0, and u1 uk is equal to 0. Then you get this. And in this case, actually, we can, if this is isomorphic to this, and then this one is also isomorphic to this. So this is a fact. Okay, so actually the statement is somehow, if this is finite dimensional over this, and then this, so then you take the generator over here, and then restrict it, and then suddenly you have this isomorphism. And conversely, if this is generated by this, and then actually you can just, maybe I can tell you the reference. And so then what does it say? So it says that this O of C 1 plus K plus N 0, 0, 0 is equal to this ideal. So this is the ideal. So therefore, I just multiply this OC 1 plus K plus N 0, 0, 0 of this df tilde of dxi, right? I is from 1 to n. And then I have another piece, this one, but this is actually this way. So therefore, here I have O of C 1 plus K and 0, 0 of df tilde, sorry, df tilde of duj. Okay? And then here, summation is from 1 j to k. Right? So you have this. So this is a germ of functions in 1 plus k plus n dimensional space. So here I have v and u and x. So that is here, right? And here I have 1 plus k, that this is v and u. So that is here. So so first I consider you df tilde and dv, right? You just consider this one, and then this is an element of O of C1 plus A1 plus K plus N, right? So this element here. Then because of this, it should be written in this way, right? So therefore, this df tilde of dv should be written as a sum. Maybe I should start from this side. So, okay, so maybe yj of, so I have only this thing. So dvu of df tilde and duj plus sum over xi of dux, because we have dux of this df tilde of dxi. So I runs from 1 to n, and j runs from 1 to k. So we just differentiate this function, then this is certainly an element here, but because of this fact, this one written as direct sum, no, this is not a direct sum. Sorry, it's just a sum. Sorry, this is not a direct sum. This is just a sum. Sorry, how to write it? So maybe just write this, and just like this. Sorry, this is not really direct sum necessarily. So this is j from 1 to n, 1 to k, and this is I from 1 to k, 1 to n, and then this one is also maybe just a sum. Sorry. And this is also, this is also, this is okay. This is okay. This may be okay. This may be okay. Okay, I don't know. Maybe just make it in this way. So sum over j equals 1 to k, because maybe there are some, relations. So therefore, this one is okay. This one is okay because I pick linear basis of this. So sorry, this one may be a sum, but anyway, so what I need is just this one can be written as a linear combination of these things, and coefficients are actually element here or here. So then you have this. Then you compare. So this one we know, and then we want to compare this. So then we want to compare this one with this one because this is the same, right? So therefore, somehow we want to consider this d phi 1 of v uj of dv is equal to yj of vu, and maybe I have to give a name here, so maybe here I. So d phi 2 of vux of I and dv is equal to this xi of vux. So now we come up with these ordinary differential equations, ordinary differential equations in v direction. So these xi and yj, we can find such a thing because of this. Then just consider this ordinary differential equation and then solve this equation. Maybe the solution exists only locally, but anyway, locally you can solve this. And then certainly you can see that if you have such a thing, and then yes, then you have this, right? So therefore you can find these things. So something like this, and maybe so my explanation may not be so precise, but maybe you may find it is in the I forgot to say Martine. Yes. Maybe there are many other. other things. But there is a book by Martinet. This is Singularities of Smooth Functions and Maps. So it is in the London Mathematical Society lecture note series, and this one is actually, they also consider maps. Maps are more kind of difficult, right? Because target is not as complex, just one dimension, but maybe higher dimensional. And also he discussed this issue over maybe smooth functions, so differential functions, and then the argument is more difficult. But analytic case somehow, you know this famous Weierstrass preparation theorem and Weierstrass division theorem, but in smooth case, you have to use a smooth version of that. That is, I don't know, Weierstrass. I forgot Weierstrass. Weierstrass. I forgot. Yes, there is an analog of this. So therefore, they have to use this. And so in this book, actually this universal deformation or universal unfolding is discussed in the, I don't know, maybe chapter 9 or chapter 10 or something. But maybe you can just look at that part and then just follow this and then you may get it. So this is somehow the importance of this Jacobian ring. So it's actually a universal parameter space of the deformation of functions. Sorry. Deformation of functions. And so this is one thing I wanted to say. And then another thing is this. Over this space. So here you consider some space B. And over here I consider B cross maybe U may be inside of Cn, with certain open set. And here you have F to C, maybe holomorphic, and with isolated singularity at origin. And let's suppose that this is actually universal. Suppose that this is universal unfolding. So suppose that this is this. Suppose that it is universal unfolding. Then actually B has nice structure. So B has so-called Kyoji-Saito's, maybe he called flat structure. And so he actually found certain metric here, and also connections, and and also the product structure of the tangent bundle. And so this one is nowadays actually called the Frobenius structures. Frobenius manifold structures. So somehow developing, I don't know, rediscovered this concept from other perspective. But Kyoji-Saito actually found this structure maybe early 80s or maybe alone. So this one is somehow something Frobenius structures. And today I want to consider this isomorphism between quantum cohomology and Jacobian rings. So today, somehow we discuss not really completely, but we discuss isomorphism between this quantum cohomology and Jacobian rings. So I haven't really probably I haven't really defined this. But anyway, we discussed the isomorphism. This is what we call the Kodaira-Spencer map. And then I need to put some bulk deformations and then deform everything by bulk class, and then we get this. And so this one, quantum cohomology, certainly people already know that there is a Frobenius structure. This one has Frobenius structure. So we have a Poincare pairing, because this is just as a vector space, it is just as a space is just a ordinary cohomology of this, and then you have a Poincare pairing. This gives a metric. So this is non-degenerate, so non-degenerate things, and then the product structure is actually coming from this big quantum cohomology. Product structure on these fibers, so T of B of this. Okay? So Frobenius manifold is somehow you have a manifold, and then you have a tangent bundle over here. Then each tangent space has a product structure, right? And also you have a connection here, and then the connection product structure is in a sense compatible and so on. But so for each point, you have a tangent space, and tangent space has a product structure there. So here, at each point B, so in our case, actually, you have this quantum cohomology. It's just a linear space. And then actually, we can only take this, but so this is one of things which I don't really know how to really formulate precisely. But if we have here the lambda 0 class, and then take a B from here, and then we have a quantum cohomology deformed by this B that I discussed last time. So therefore, you have such a thing. And then it also has a natural connection here, that is the Brovin connection and so on. So you have such a nice structure here. On this side, actually we don't really know so much. But in the case of functions, case of usual functions, then he actually cook up everything. So from so-called what he defined primitive forms. And primitive form is not unique, but if you pick one primitive form, then you have a flat structure. And the existing primitive form is also difficult. I actually do not follow the proof in this. So therefore, there is a result that if you have an isosimilarity at the origin, and then you have this, and then you have this. And so this side, we expect something similar to that. So this is a story for usual holomorphic functions, but we may expect some Frobenius manifold structure as in holomorphic maps, holomorphic function case. And this is actually a ring, right? So we have a ring. It's a ring structure because it's defined as a ring, so therefore it's okay. And then, so we don't know what the ring structure. It's a ring, so this somehow we established already. So here we have this quantum cohomology, and it has a natural product, and here it's defined as a ring, and then we have isomorphism between them. That means this product and this product actually match up. For the pairing, so we have something which I also want to discuss today. So that is some sort of residue pairing. But we can only somehow show the correspondence in so-called semi-simple case. So this I also discuss a bit later. And then after this, probably we haven't really explored so much. So therefore we don't really know this. But somehow we expect that this gives you some Frobenius manifold structure, and so this may also have Frobenius structure. Then we expect these two may be isomorphic as a Frobenius manifold. So this is somehow the stories which we may explore sometime. And so yeah. So this is the reason why I just somehow summarize, or maybe just mention this universal unfolding story. Okay. So now I just stop here and then move to the discussion of this one. So again, I use these bulk deformations. And this provide a Spencer map. So this is called Spencer map because it's also some sort of deformation theory. So therefore, people may call it Spencer map. Okay. So in our case, I start with xj omega. This is a compact scalar toric manifold. And then I consider the following. So our infinity structure here, mk. And then we can, if you have a B from this cohomology of X with lambda 0 coefficient, then we can deform it into another infinity structure. So I consider operator Q, maybe Q of Lk, and then take beta here. And so this is a map from cohomology, or maybe better to today, maybe I may be more precise. So here I may start with A of X with this lambda 0 coefficient. So this is actually the module, lambda 0 module generated by the toric cycles, torus invariant, T torus invariant cycles in X. So we have a toric manifold and we consider all toric. And then I take this H1 of this LU, and then here lambda 0, tensor, sorry, here take tensor L and tensor K, going to this, sorry, this one is also not H1, but everything at the moment. So like this. So namely, I consider the moduli space of border stable map, genus 0, and L many interior map points. So this is a number of interior map points. And then K plus 1, it's a boundary mapped point. And then representing class beta. So beta is always from H to XLU with Z coefficient. So we have such a thing. And then we have a map to X X by F plus. So I have a L mark point. I take evaluation at those mark points. And also I have evaluation map to L L. So here I have a K many of them. And then I have a map to this. Sorry, yes, like this. And so we actually cut out this modular space by these things. So I take P, I don't know, P is from this A, X, lambda. It may be better to say something, but okay, so lambda 0 of L. And okay, and then sorry, maybe better to better to forget about this. So just usual things like over integers. Just they are actually bunch of torus invariant divisors, and then I consider moduli space. So maybe better to write it as a P1 tensor PL, and those are torus invariant cycles. So just consider this, and then LK plus 1 beta, and then I take a fiber product of this. And fiber product is taken over K product of K copies of, no, product of L copies of this. Okay, so I consider this. I take this and then take a fiber product. Namely, these mark points are mapped to these P1 to PL. Right? Mapped to points in these things. So I have some modular space. And then here, now I have an evaluation map to L, K many things. And here I have F0, just one. And then pull back torus invariant differential form here, and then push out this torus invariant form. And so therefore, this gives us correspondence, gives us operation on the torus invariant differential form on L, K copies of this to just torus invariant differential forms. So this is actually our this Q F something. Okay, so QLK beta is a F0 streak composed with this F star using this modular space MK plus 1, MLK plus 1, beta, and then take a fiber product with P1, PL. So this is one. And then we consider B from this cohomology of X with this lambda 0 coefficient, and then we just write it as a linear combination of these P's, a basis of the torus invariant cycles, and then just extend it multilinearly. And so we define this M, B, K is equal to the sum over inverse of L factorials. And then here I have Q, L, K, and here I take this thing and this thing, right? So roughly this is definition for this variable deformed infinity structures. And so then, because when we study the Maurer-Cartan equation on the toric manifold, torus fibers, without variable deformation, we actually show that this H1 of Lu with this lambda 0 is actually contains this MC weak tilde of this Lu. So this actually we saw, and argument goes through the same way in this because this P1 to PL, those are torus invariant cycles. So therefore, after taking fiber product, this one is also it has a torus action here. And then this one is they are torus orbit, and these are equivariant. So therefore, previous argument goes through. And so we also have this after introducing these bulk deformations. So this is the same thing. So we can consider potential function of B on this. So we also have potential functions, bulk deformed potential functions. So this one is originally function on this. Okay. So this is just the following. So if you add MKB, this is both B, and then take small b from here, right? So small b from here, and then take this, and then sum them up. And then this is equal to this potential function B of this B, and then the unit, like this. So we have this. So now we want to consider this Kodaira-Spencer map. So maybe better to write it in a, here. Okay. Spencer map, maybe I start from here, this A of x lambda 0 to, I have to introduce something here. So I don't know, maybe last time I didn't really introduce this yet. So maybe I will introduce this, and then I have something like this. And here is a map here, and here is a map here, so that they commute. So we want to consider this sort of diagram. I haven't really told you this. No. So this I have to model out by this. So then here I have yi and dpob dyi, and then I have to take a closure with respect to this. So I will define this. So this is in the Fano case. Maybe you just consider it as a Laurent. This is Laurent polynomials. But here we may have infinite series. So therefore, instead of Laurent polynomials, we introduce certain replacement of that. And so then I haven't really defined it, but somehow this. And then because cohomology is smaller than this, right? So you have a torus invariant cycles which represent the same cohomology class. So therefore they are not the same. So there is equivalence relation here, so that after certain after such equivalence relation, you get this, right? So at the beginning, I defined the mapping from here to here. And then, so if you have two torus invariant cycles, then how the image changes? So the difference actually only in this idea. So therefore, this map descends to this map. And we will see that this one is a ring homomorphism if we introduce here the quantum cohomology structure. And yes. So, but anyway, as a vector space, it's a quotient of this, and then we want to define this. Okay. So why do we need this? So last time, in the final case, what I said is this potential function of this y1, yn, without bulk deformation is something like this, right? Sum of y1 and v1 j, yn vn j times t to the power minus lambda j or something. So it was such a Laurent polynomial. So therefore, this actually in Laurent polynomial. So you can just think of it as element in this. Because you have only finite many terms. But in general, we may have many terms. So namely, when we prove this, actually what we studied is somehow this mu of beta has to be 2 or something, right? So maybe without bulk deformations, actually only mass of 2 disks, mass of 2 border stable map contribute to this. And the final case, they are only these basic classes. But in general, you may have more general toric non-final case, and then there may be some rational curves of negative Chern number. So Chern number, so evaluation of C1 with some class. So A maybe from this H2 of X Z, and this may be negative. So here there may contain some negative rational curves, and then if you have this disk of maybe more complicated disk, I don't know. I cannot really write how it is, but maybe there may be some rather complicated disk. I don't know. Maybe like this. Then probably this one has very high Maslov index. Like here, if we intersect this and this, then Maslov index must be 6. But if there is a negative holomorphic curves, negative rational curves, then you may add such a thing, then maybe they may add up to 2. So you have several components, like a disk component and sphere component. And to the Maslov index, actually disk is nothing but intersection number with these divisors. But rational curve may completely contained in the toric divisors. And then in such a case, actually those rational curve contribute to the Maslov index by 2 times Chern number. So therefore it is negative, and then although this disk part is positive, bigger than 2, because of this, they may also contribute to this. So therefore you may have infinite many terms. So once you have this, once you have holomorphic curve in this with this property, and then a priori no reason why we have finite sum. So therefore we need to consider certain infinite sum. Okay. So then it cannot be such a Laurent polynomial ring. So okay. So in non-final case, so maybe even without bulk deformation, there may be infinite many mass of 2 classes represented by bordered stable maps with genus 0 and connected boundary. And so therefore, then in such a case, this potential function is not really in these things. Sorry, not only this, right? And it is not really a formal power. If you have only positive powers, then you can talk about formal power series. But here, it may have negative ones. So you have positive ones and negative ones. If you have infinite many of them, then you cannot multiply them, right? So therefore, just simply taking a all infinite sum, you cannot get a ring. So we need something different. So then we use this polytope to do something. So, okay. So, but anyway, so we just don't consider something. So let's consider formal sum, just a formal sum. I don't know, maybe somehow A of I and Y of I, right? So A of Y is in this lambda, say, and I is just a element from Z to N, right? So you just consider such infinite sum, and we consider some condition so that if you consider infinite sum with certain relation, certain constraint, then such collection actually gives you ring. Okay. So how can we do this? Okay. So in fact, we consider following. So we consider this polytope P. And then I take any element U here. Then we want to consider the following. So let's take Y from this. So this one is maybe Y1, Yn. Each of them are non-zero element from lambda. And then we want to plug in this to this. And ask whether this one converges or not. So, okay, so I take this, and then suppose that this U is an image of variation of this. Like this. So each element here, and then from here to here, you have a variation, right? So variation is just to take a lowest order term and then read off its exponent. So this is variation. So just consider this. And then you may ask whether it converges. So ask whether this one converges in t-addict topology. So this is the idea. So somehow we consider formal power series, they are all possible infinite sum, but we consider infinite sum so that if you plug in element y with variation u, then this one converges to something, converging lambda, right? So then maybe if you have two such things, then you can also do this. So what does it mean? So maybe, for instance, you have I, so therefore I may just denote it. So I may be this I1, IN, right? So they are positive or negative. So we may consider the sum of absolute value of this. And if you bound this by something, and then you have only finite many terms, right? So somehow we consider the limit as this one going to infinity, then something may happen. So then this variation of AI times, so maybe I have to write it more precise. So I1 of variation of y1 and In of variation of yn, plus tends to infinity. Okay. So it's infinite sum. So therefore, we just order them as this according to this quantity. So we just order them so that, if you start with 0, 0, 0, and then 1, 0, 0, and minus 1, 0, 0, and so on. You have only finite many terms. If you just consider bound for this, you have only finite many terms, right? So first you start that this one is 0, and you have only one term. If it is equal to 1, you may have 2n terms. And then if it is bounded by 2, then you have more terms. But anyway, you have finite many terms, right? So just consider group of such things, right? Let's order them. So then if this sum tends to infinity, then we just consider variation of each component. So here the variation is this one, and this one certainly, if you have a product, then so variation has some property, right? Pt of A and B. Certainly we look at the exponent of lowest order term, so therefore we have this one. So if you consider this yi, and then this is variation like this, and variation is like this. So therefore, if you take the variation of this, then this one is this. Okay. So because this one has variation like this, and this variation tends to infinity, then it converges in t-addict topology. So this is by definition. So the t-addict topology, the topology is defined by variations. Sorry, maybe I have to say this. So now we have this lambda to r and plus infinity. So this is Vt. So actually here if 0 is going to plus infinity. Okay? And then maybe I denote the norm. I don't know. Maybe I may denote this one. Maybe t-addict topology is by exponential of minus of Vt something, right? So if you put 0, then this one is minus infinity, so therefore it is 0, right? So you have this variation, we consider this. And then this becomes a norm. So actually if you consider distance between two elements, A and B, I just want to define it as a variation of A inverse. So this gives you a metric. So t-adic distance. So therefore, yeah, I'm talking about convergence t-adic topology. That means we have a sequence element in lambda, and then we can put a topology by using this, and then ask whether this one converges in this topology. Yeah, if you have this, then each term actually the kind of absolute value tends to 0. And so because this is no Archimedean case, so therefore it converges. Okay. So for each u, we can ask whether, and also, sorry, and this one is equal to u1 to un. Right? So I take a point u, and then consider the element y with variation u, and then somehow consider this condition. So maybe now this is kind of motivation. So okay, so now I define this. So for each u from this Rn, we can consider the following condition for this infinite sum ai and y and yi. Right? So consider, ask whether the following. So as I1 plus in tends to infinity, then the sum like a vt ai plus this I don't know, ip of up, summation of a p equal to 1 to n tends to infinity or not. Okay? So we can consider such a condition. For each u, you may consider such conditions. And so if you have two infinite sum with this property, then if you multiply them, still it has such a property. And so in our case, actually, if we take u from P circle, for any element from here, ask whether, so we require that if I1 in tends to infinity, then the sum of variation of ai plus sum of ip of up, p equal to 1 to n, so u is equal to u1 to un, right? Tends to infinity. So we consider this condition. So maybe I consider this condition. Okay. So somehow we consider this condition. Yes. Yes. So we consider this sigma ai ui, sorry, ai yi satisfying this kind of condition. You may also consider boundary point, but they are little different conditions. So if you correct them, somehow we have this lambda y1, yn, and p circle. Yeah, this one is a little bit strange, but yes, this one is interesting. So sorry, maybe I start from, yes, maybe I start without this and then without this. Then this may be easier. So at this moment, probably you don't you don't see the difference, but somehow this is the one. Okay. And so this is one of the motivations of our things. So consider this and then this. Why we want to use this? Because if you have a potential function, it may, so potential function of this then it may be, there maybe we have infinite many terms, right? So I don't know, maybe ni and yi, I'm sorry, ai, yi, something like this. But somehow we have infinite many terms, but this ai somehow contains the following. So this is actually the t to the this, right? So we use the moduli space representing class beta, and then we always put this term, right? So if I have point u here, and then we consider holomorphic this border stable maps, then always we consider such a simplex area of border stable maps. So then usual case somehow if you consider then you consider kind of Gromov compactness theorem. So if this one is bounded, then you have only finite many terms, right? So if you have infinite many terms, then this exponent must diverge. So therefore, using Gromov compactness theorem, so that means if you have m beta j, which are non-empty, then this beta j omega has to diverge, right? Only find the many terms. So therefore each term somehow coming from this. So therefore you have this effect here. So therefore it actually diverges to infinity. So if you consider this Lagrangian torus phi by Lu, then in fact this area, so I don't have, but so for this apply the Gromov compactness for Lu, then actually you can get a convergence at U. So you can be anywhere in the polytope. So U is just the interior map point, interior point. Then you have a corresponding Lagrangian torus, and then apply Gromov compactness theorem to this, then it converges, right? So in fact, if we have U here, if we have another point U prime, then you may wonder whether the term appearing here are related or not. But they only differ by this one. The reason is simple, because here I have a torus acting on it as an isometry. But certainly toric manifold, we have action of this one. And this one acts here holomorphically. Right? Simplex form certainly not preserved. But so you have a holomorphic map here. Then applying this cysteine action, you get another holomorphic curve. And if you have 2 points here, you have a 2 inverse image of these interior points. So 2 torus orbit, 2 compact torus orbits. These are actually related by certain element from cysteine, right? So because cysteine actually acting here, it's actually here in interior. I don't know. Freely and homogeneously. I don't know. So cysteine just corresponds to the interior of this, and action is just multiplication. So therefore, it's here freely. I don't know how to say freely transitively. Yeah. And so you have one torus orbit here, and then consider image under this action, you get another torus orbit. So therefore, if you have a border stable map with boundary here, then you also have a corresponding border stable map here. So therefore, the contribution actually this is a kind of number of such objects, but we also put this effect. So this one depends on the location, but number doesn't depend. So therefore, yeah, so if you change this, then only this term changes. So anyway, so if you apply this Gromov compactness for all points in the interior polytope, then actually this condition is satisfied. But then I have to take an interior somehow. Yeah. So that is a little bit different. But maybe I just want to say this. So maybe what I want to say is the following. So okay. So apply the Gromov compactness theorem. For this LU, and U may be from P sample. And then from here, actually this potential function, y1, yn, converges at this U. That means, more precisely, this P of y1 yn converges in T-addict topology if the variation y is equal to this U. Okay? So therefore, actually our function, potential function, actually live in these things. Okay. And I want to give you more easier way to understand this. I don't know easier or maybe a bit different way to understand this. So this is the following. So I have now this lambda, and then I consider this z1 zm, right? And then I have a map to this lambda y1 plus y minus 1 yn plus minus 1. So we just define this as a gj is mapped to the sum of y of v 1j yn v and j times t to the pi, something like this. And we somehow notice that this is actually surjective. This is surjective because these vectors span Rn, right? Because this v1 vn, vm element from this, the lattice n, actually the span this n, right? Span integral lattice. So therefore you can actually make it a surjective map. And then kernel was this quantum Stanley-Reisner relation. So anyway, you know this. So this is just algebra. So okay. So I just want to keep this. Yes. So then maybe I just erase this. Maybe I put it right here. And then I consider this lambda z1 zm. Maybe this may be easier to define. So this one is this. So if you have this like again, I don't know, maybe bj and zj, and j maybe from this now here, sorry, m. And we consider this thing so that if j tends to infinity, this v of t of bj tends to infinity. I think this is okay. This is okay. Yes, this is okay. So this is not all formal power series, but only consider infinite sum of this one. And then after this one is also mapped to this. I think this one is mapped to this. Yes, yes, yes. So just here we have this metric, and here we also have a certain metric, because here for each u, we have some norm. So for each u we have some semi-norm on this lambda, maybe y1 plus minus 1, yn plus 1. But we consider the set of norms. So here I have just one norm, and here we have a set of norms. And then this is actually continuous, and so therefore we can take a closure. This map is continuous. So then we take a closure, and then we have this map. But here we may consider just a formal power series. So formal power series without any condition. So therefore this is actually contained here. And then this one is somehow mapped to lambda y1 plus minus 1, yn plus minus 1, and then this is something like this. So this part is a little bit delicate, and maybe I have to check it somehow. Okay. But anyway, so this is okay. So I haven't really defined this. I define this. So I define this by this. I consider all infinite sum with this property, and then you get this. Okay? But for the interior Polytope, actually this one is bit subtle. So therefore, I don't really right now give you such description. But somehow we can say that this is the image of this. So somehow you can extend it to this. So there is something like this. And okay, so this one I explained. Maybe this one, maybe if I have time, or maybe I can explain later. So potential function is actually, as I said, this. If you take a point from the interior, then it converges. So therefore, maybe easier to find the potential function stay here, in fact. But if we consider potential function without bulk deformation, or maybe only bulk class is degree 2, in such a case, actually the potential function actually live here. And so, potential bulk class actually all lambda plus bulk class, and then it stays here. Sorry. So if bulk class is from this H star of x lambda plus, and then actually the potential function stay here. And if we consider the complex coefficient, and then may not be here. But anyway, so this may be little bit subtle. But anyway, so I have this. And so we have a Jacobian ring. It's just, in fact, it is also quite subtle here. I have to put lambda 0 here. No, sorry. I have to put so this part is rather strange. So I didn't really introduce this, but then here I consider this yi dpo d of dyi, and then take its closure in this periodic topology. So yeah, so this is a little bit complicated things. So therefore, maybe you just think that we have a kind of power series ring which behave like a Laurent power series ring, and then inside of it we consider the Jacobian ideal, and then if you consider the quotient by such a Jacobian ideal, yeah, you may have this. So in the Fano case, you don't need to do this, but if you are non-Fano case, like even this Neff case, I mean the field of surface degree 2, then you need to take some closure here, because otherwise you have a critical point outside the polytope. So you have to throw away something. So therefore, somehow you need to take closure of it. But anyway, so yeah, this is a little bit complicated thing. So therefore, I just want to move to this Kodaira-Spencer map story. So I have a potential function first of this. And so this is a family of functions. This may be considered as a family of functions parameterized by this B. So if you remember somehow what I want to do is something like this. So here I have a, if you remember my first topic I discussed today. So if you remember the first part of my talk, and then, so here we have a potential function of x. I don't know, maybe like this, 2 lambda. Okay. So first part means this thing. So here you have ck, and here you have a ck times cn going to c, and this is maybe f. This sort of story. So here instead of this, I consider this, and the domain of function is actually this. So namely, I consider, yes. So element here are infinite powers, infinite sum, so that it converges at some point in the polytope. And so they move inside of this. And so this is the domain of our potential function. So this one is actually defined this way: P of t to the x, and b and y is equal to potential function of x, bulk deformed by y. Right? So I take a bulk deformation of potential function, and then we consider it such a family of functions. And then we want to consider the infinitesimal deformation of this. So namely, if I take A, so now I consider the map, right? So this. Sorry. Not yet. So I will say this, but maybe before that, actually, this one is not this. Sorry. This one is not yet this. So I consider bit bigger one, so that is A of x of lambda 0 here. Sorry. I will come to the point later, but so anyway, consider this. So yes, yes. Two. Yes, like this. So we want to consider such a thing. So in this story, what I said, if it is a universal, right? If it has a universal unfolding, right? And then if we have another one, like a CA, and CA times CN going to this, then what we want to have is somehow map from CA to this CK. Over there you have the CA times Cn going to CA, CK times Cn, so that this function G is actually the pullback of our universal family, right? So we want to do something similar here. So here we consider some Jacobian ring, because in the finite dimensional case, in a holomorphic function case, we consider this base space as a Jacobian ring, the basis of Jacobian ring, and then here we have another family. So now we have a family of functions, right? So this is maybe you may expect that because this has the same name, maybe this Jacobian ring, so therefore it should be kind of universal object. And here, so what we do is this. So you have A here, and then we want to consider the deformation of this guy in that direction, maybe epsilon times A, and then just take a derivative with this, take epsilon equal to 0, then you may have this map. We want to consider such a thing. Okay? But in fact, we have better situation because, we have, maybe I should write this. Before really modding out, I have actually a maybe P circle or something. So actually we have this kind of map. So here I have A, and then you just take this dd epsilon as epsilon going to 0, and I have a function P of x, and B plus epsilon A, sorry. So without taking an equivalence class, we have something like this. And so this one I still have it here. So this is the Kodaira-Spencer map on this level. So I take an element from A here, and then I consider the directional derivative of this potential function in this A direction. Then you get this map. Okay. But also I wanted to have a map from here. So one way to get it somehow easy way is somehow you take a splitting here, and then take a splitting and then compose with this. Certainly you have a map from here to here. But certainly it depends on choice of splittings. So if you take a different choice, and then you may have a different element here, so somehow you may want to know how they're related. Okay. So this is the Kodaira-Spencer map, and so I just want to say that if you have two elements which are actually homologous, cohomologous, and then the image differ only by this Jacobian ideal. So I think I can, I still have any other number, so therefore I can We can discuss this. Okay. By the way, these rings are so-called these are maybe our notation maybe strange because we may need to double I don't know brace. But anyway, this one is so-called strictly or strongly, I don't know, strictly convergent power series ring. So it is actually called strictly convergent power series ring. And this is, yeah, okay. So now I want to show how they're related. So first thing, so if I have Q and Q prime, they are homologous. So namely, Poincare dual class of Q and Poincare dual class of Q prime are cohomologous. And then how these things are related. So Ks tilde and Ks tilde of Poincare dual of Q minus Q prime actually contained in this ideal. So like okay, so this somehow I want to show. And if it's the case, then it descends to this quotient. Okay. So the argument is somehow kind of natural, but maybe to give a detail maybe a little bit complicated. But anyway, so now I start from this. So by assumption they are cohomologous. So their homology classes are actually cohomologous. So therefore, I consider maybe I have to take either Q minus Q prime or Q prime minus Q. So, okay. So let's assume that this one is equal to boundary of something like R. So R is actually a chain in this X, so that they are, they differ by the boundary of this. And now we started from Q prime, both are torus invariant cycles, but R cannot be torus invariant cycles. So therefore, this one is not torus invariant, right? So up to now, I only use the moduli space, which somehow always carry torus action. But now we have to somehow use something which is not torus invariant. But anyway, we use this. And then consider the following moduli space. Okay. So I consider moduli space maybe L plus 1, K plus 1, and representing class beta. And then here I take a version map at integral map points. And then here sorry. What better? Okay. So, okay. So for simplicity, just put it as a, I just give a name for this. Maybe just P. Yeah, okay, just P. Okay, P here. And then, notation is a little bit different, but maybe okay. And then, okay. Yes. And then maybe I consider something like P, P, and then finally I put this R here. It's a fiber product taken over this. So maybe I denote this space as, maybe I don't know, maybe M, A plus 1, K plus 1, and here I have beta, and then P tensor L, and tensor R or something. And then I want to do the things, right? So I always consider M, L plus 1, K plus 1, and this beta, and one side is P, tensor L, tensor R, and then I have a map to L, and then map to this. And now I take the boundary of this. So there are several kind of boundaries. So this is codimension 1 boundaries. Has several types. And the first one is somehow, instead of R, this is a chain, right? So therefore this one may be replaced by the boundary. So the first type, maybe last type, I don't know, maybe the first type is just M, A plus 1, maybe K plus 1. And here I have beta, and then P tensor L, and then finally I take this one is R. So this one is now P itself. Okay. So if we, so first type boundary is somehow boundary of this. You take a fiber product. So what I'm saying is, if you have a space. Like if you have two spaces, and then the boundary of this one is equal to the boundary of x times y, and x times boundary y. Right? And if you take a fiber product over B, so that B has no boundary, if you have no B has no boundary, and then this one is either this or this. Otherwise, you have a boundary with the base, but these two things. And so I have a fiber product, and this side, they are cycles, so no boundary. But this one has boundary, so therefore I have this. Right? So this is this replace R by boundary, and then you get something like this. But then this one is exactly the but this one first. And second type is actually coming from this type, right? But then you have a moduli space of holomorphic disks, and then you take a boundary of this, and then maybe it may be decomposed into something like this, M beta prime, and then maybe other beta prime and beta double prime. So namely, I may already mention it some time ago, but so you have a disk like this, or maybe even with sphere component, it may be decomposed into two disk things. Sphere bubbling is actually codimension 2. So therefore, if you consider codimension 1 boundary, the sphere bubbling is not really contribute to this. So this is actually codimension 1 things. And so, maybe I have a 1 mark point here and 1 mark point here. So this one is this one. Okay? Maybe if I put a mark point like k plus 1 mark point, and then maybe here I have a k1 plus 1 mark point, and k2 plus 1 mark point, and then k1 plus k2 is equal to k plus 1. So this, you can consider this in arbitrary ways. And now I have two cases. So maybe I have here ML1 plus 1. I don't know, maybe ML1 and K1 plus 1 of beta prime. And then everything is this L1. And then fiber product over L of M L2 and K2 plus 1 and beta double prime and P L2. Sorry, maybe better to write L2 plus 1 here. Plus R. So this is another thing. So here in this case, actually K1 plus K2 is equal to K plus 1, and L1 plus L2 is equal to L, and beta prime plus beta double prime is equal to beta. So you consider all possible degeneration like this, and then you have several interior mark points, and then it may be somehow distributed in either side. And if you have a boundary mark point also may be distributed on the boundary of either component. So you have this. So then on the boundary somehow it respects the cyclic ordering. So therefore here it also should respect cyclic ordering. But for interior mark point, in fact it is not the case. So therefore interior mark point, some sort of shuffling may happen. So even though I wrote in this way, somehow some sort of shuffling may happen. And third type is this M L1 plus 1 K1 plus 1 of beta prime and P tensor L1 tensor Q tensor R and then L and M L2 plus 1 and K2 plus 1. Sorry, L2 and K2 plus 1 of the beta double prime and P tensor L2. Yes, like this. So the difference is somehow in the second case, R is in the second factor, and first case, the third case, R is in the first factor. Namely, we have a specific mark point Z0. So Z0 is a point we take evaluation map this. So this is kind of special point. So here I have Z0 and then either component have Z0. Yeah? Z0 may be this component or this component, but anyway, Z0 specify one of the component. And then other map points are mapped to P, but one of them is mapped to R. And then you may ask, in which component R is intersecting? So if R intersects this part, that is the third case. If R intersects this component, then this is the second case. So these two differ by this. Okay. Then I may start from maybe third case. I may start from third case. So in third case, so maybe I should stop now and then continue. Okay, sorry. No, actually I completely misunderstood. So I thought that, yeah. Okay, so I have to stop now, yes.